Happy day, students. How are you? In our last class, we were discussing about electric field and potential difference, right? So we are going to continue with that only. Let's see what are the other things we can study in that. See then, I'll make one question over here. Okay, here is V and here is X or R, you can say. Okay, and the graph is like this. Okay, this let's say is position R1 and here is position R2. My question is very simple. If suppose we are talking about position 1 here and this is position 2, you have to tell me where electric field is acting in positive x-axis direction, where electric field is acting in negative x-axis direction. Okay, that's a point 1. Where is electric field acting? How to find electric field from here? We know that we have one relation which says E equal to minus dV by dr. And if you look at this particular thing, that is actually slope. So that means negative of slope of this particular curve. So see over here, if I am going to see the slope, this is the tangent to the curve over here and this is x-axis. So this is the slope. And you can see that this is positive slope. So if the slope is positive, dV by dr value is positive, that means electric field is negative. That means where is electric field here? Electric field is towards negative x-axis. Okay, let's talk about point 2. Point 2's tangent is over here. Okay. Then this tangent is negative or positive? It's negative. Okay, this angle. Okay. This angle you can say, or if suppose you want to take it from the other side, your wish. It'll be like that. So it depends like how you want to take, but its a slope is negative. So if the slope is negative over here, that means electric field will be positive. That means electric field will be acting along positive x-axis. So I could have asked you another question in this. If suppose that a charge Q is kept over here. Okay, so where is the force acting on it? Obviously force will be acting towards left here, and if the Q charge is kept over here, force will be acting towards right. Okay, so these kinds of questions also can be asked on electric field and potential relation. What are the other questions? That also we are going to see now. Okay, first I am going to ask very simple question. As we already know that electric field actually acts from higher potential to lower potential. Okay, so if suppose that we say in this zone the potential is 20 volt, here is 10 volt, okay, and I have to find electric field between them. The gap between them is 0.1 meter. Okay, so how is the electric field? Electric field between this, again the formula is same only for us, minus delta V by delta R. Okay, this is the formula. So here E is equal to minus V final minus V initial, that is 10 minus 20. What is the gap? Gap is 0.1 meter. So what we are going to get? E is equal to 10 by 0.1, that is 100 volt per meter. The simplest question. Okay, build up on this only. If you are going to see other questions in which electric field is inclined. Okay, electric field is given inclined, that means it's making an angle with the x-axis. Then how to find it? Let's see. How can we find it? So electric field is given like this. Okay, its value we can let it be E0. Okay, it's given like this. Okay, and this is making an angle with x-axis, let's say 45 degrees. Okay, in this time I want to find the potential difference between 2 points. Where are the 2 points? Let's say we can say a point is somewhere here and its coordinate we can say is 1, 2. Okay, and another one coordinate maybe somewhere here we can say. Okay, its coordinate let's say is 4, 6. Okay, electric field is given like this, making 45 degree with x-axis. Okay, a point A is here and a point B is here. So I have to find potential difference between these two. So I want to find VB minus VA. Okay, and VB minus VA actually is what? Minus EDR or minus E delta R. Right? This is the formula. So whenever this kind of a question is coming, we will be going for the vector route. Okay, vector method only, because that is going to make the problem also easy for us and it will give us correct answer also. Depending on the options given. If suppose the option wants only the magnitude, we can find from the vector magnitude also. So there is no problem in it. Okay. So what we can do is we have to write E vector. Now what is E vector over here? We can say that E naught is the magnitude. It's making an angle 45 degree with x-axis. So vector E we can write as E naught cos 45 I cap plus E naught sin 45 j cap. That's vector E. Yes or no? Correct. Now I want delta R. Delta R means R2 minus R1. So its position vector we know, we can write this as 4I cap plus 6j cap. Whereas this one we can write as I cap plus 2j cap. So delta R, which is actually R2 minus R1, can be written as 4I plus 6j cap minus I cap plus 2j cap. Okay, so what's coming? That is 3I cap plus 4j cap. 3I cap plus 4j cap. So we can put over here what is VB minus VA. VB minus VA equal to the dot product. Now dot product means what? Dot product means is I cap will be multiplied with I cap, J cap will be multiplied with J cap only, right? So E naught by root 2 into 3. So we'll be writing 3 E naught by root 2. Okay, plus again E naught by root 2 into 4. So 4 E naught by root 2. What are we getting? VB minus VA is what? We are getting it as minus 7 E naught by root 2. What this minus indicates over here? Minus indicates that VB is less than VA. Okay, VB is less than VA. So VA is greater than VB and its magnitude is 7 E naught by root 2. And what is the unit? Volt. Okay, unit of potential difference will be volt. Okay, few more questions are there, we can solve them. What are those questions? But that we will see after doing equipotential surfaces. Okay, so now let's discuss about equipotential surfaces. Alright, what is equipotential surface? What the name is suggesting? Name is suggesting that those surfaces which are at equipotential, that means same potential, those are called equipotential surfaces. Okay, what is equipotential surface? A surface on which potential is equal or electrostatic potential is same. Equipotential surfaces. Okay, so what you will write? Surfaces which have same potential everywhere. Or we can say what the definition is given in books. In definition given in books is locus of all the points. Locus of all the points which are at same potential. Which are at same potential is called equipotential surface. Okay, right? Three types of equipotential surfaces are there, very similar to what we have already studied in wave optics. In wave optics we call them as wavefront. Okay, there what was the definition of wavefronts? Locus of all the points which are vibrating in same phase. Here what it is? Locus of all the points which are in same potential. Okay, so similar to wavefront, here also we have three types of equipotential surfaces. What those are? One is a parallel or a plane surface, flat surface, okay, a plane surface. Do you remember when we used to get plane wavefront. Plane wavefront, we used to say that when the source of light is at infinite distance, okay, then the rays from infinite distance become parallel. And we know that the light rays are always perpendicular to wavefront. Yes or no? Absolutely same thinking here. Plane equipotential surface when it is possible, when the charge is kept at infinite distance. Okay? When the charge is kept at infinite distance, then in that case equipotential surface will be a plane surface. And like there, rays used to be perpendicular to the wavefront. Here, electric lines of force will always be perpendicular to equipotential surface. Able to understand? Okay, so plane surface is the first one. Second one, as you know that wavefronts was spherical, so here also spherical. Equipotential surface will be there. And third type was cylindrical, so here also cylindrical surface. Okay, all three we are going to see right now. So see them. See them and try to understand it, okay? So suppose that we have electric field like this. It's a uniform field I am making, and these are lines of force. Okay. This is uniform electric field and these are lines of force. Now if I choose here, if I say this is point A, okay, and this is another point here, and this is another point. Okay, let's say this is B and this is C. And if I ask you what is the potential at point A, point B and point C, and what is the relation between them? Okay, electric field is like this, from here to here it's moving. Okay, so we know that all these points, okay, are perpendicular to the electric field, right? And since electric field is along x-axis, they have same x coordinate. If suppose that I say x coordinate of this is 1, so its x coordinate is also 1, and its x coordinate is also 1. Okay, all three have the same x coordinate. Have you moved an inch towards the electric field in the direction or in the opposite direction? No, you haven't moved. Okay, because we know that potential difference will come only when you move in the direction of electric field. If you move perpendicularly, if E and dr are perpendicular to each other, and you see that here what it is, you are moving from here to here. Okay, that's perpendicular. So what is the angle between E and dr? 90 degrees. So if 90 degrees here, we can say that dV equal to 0. That means there is no potential difference. That means point A and point B are at same potential. Okay. So A, B, C, all three are at same potential. Now what we have to do is we have to combine all this to make a wavefront. How will be the wavefront? Just see. Okay, I am making a wavefront. So I am joining all these 3 points. Okay. And making a plane surface. Something like this. So all the points on this plane surfaces are at the same potential. Same way, if another one I make over here, okay, one more. So something like this. Okay, these are all what? Equipotential surfaces. Which type? Plane. These are equipotential surfaces, but plane surfaces. Okay. Now the question is, when electric field will be like this, parallel to each other? Again, the same theory what we studied in wavefront. When the rays used to be parallel, when the source is at infinity. Exactly same way over here. If the charge is at infinity, the line of electric field will be parallel to each other. And then what kind of equipotential surfaces we are going to get? Equipotential surfaces. Right? Now, let's talk about spherical surfaces then. When we are going to get spherical? If wavefront we are going back, then if there is a point source, okay, then we are going to get spherical surfaces. Here also, if we have a point charge, then what we can do? We know that from here at r distance, I will be getting what potential? 1 by 4 pi epsilon naught q by r. Now is this R need to be along x-axis only? No. It can be in any direction. This only will be the potential. So here at R distance also, here at R distance also, here at R distance also, towards me with R distance, away from me at R distance, everywhere potential will be same. And if we are going to join them, we are going to get what? Sphere. Okay? So that's the sphere over here. Sphere of radius R. So this is spherical equipotential surface. Okay? It's a spherical equipotential surface. Right? Can make one more. Here is, suppose potential is V1, then you can go further apart. You can make another sphere like this. Here potential is V2. Here and here potential is different, but on this surface entirely potential will be same and it will be equal to V1. Same for V2 also. Okay, let's see third one then, cylindrical. When we are going to get cylindrical, again go back to the wavefronts. When we got the cylindrical wavefront, when the source was line source. Okay, line source was there. Here also, if I am going to have a wire, okay, wire which is having uniform charge density, we used to take lambda, okay, and if you remember, because of lambda we found electric field also at this point, right or not? So if it's infinite, then what we are going to get, we will be getting the electric field here, 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 same on. Okay, and same way potential also will be same at equidistance from the wire. So what if we are going to make equipotential surface? It will be what? It will be a cylinder only. Okay, across this entirely potential will be same. Okay, so if suppose here is potential V1, then again we can make one more. Okay, like this. On this one will be potential V2. So on this cylinder, inside cylinder potential will be V1 and outside cylinder potential is V2. But remember that this is because of line charge. Okay. So three types of equipotential surfaces. Now what are the positives of equipotential surface, or what are the properties of equipotential surface? As usual, two equipotential surfaces cannot intersect each other. First point, okay? Two equipotential surfaces cannot intersect each other. Okay. Second point, electric lines of forces are always perpendicular to equipotential surface. Okay. Electric lines of force are always perpendicular to equipotential surface. Let's see in this one. Now I know that if the charge is at the center, then electric field will be radial. Okay, it will be radial in this direction. And this is the equipotential surface. If I am going to make a tangent over here, see that what is the angle? 90 degrees. Same way this one also you see. This is how the line of force is, or electric lines of force. If I am going to make a tangent over here, it will be like this. This is 90 degrees. Okay, if you see over here also, here electric lines of forces are like this. Make a tangent on this surface. See what is the angle. In the plane one also I have shown you already. And that one also, the plane surface, equipotential surface was perpendicular to electric field. Okay, that's very important point. Electric lines of forces. Electric lines of forces are always perpendicular to equipotential surfaces. Equipotential surfaces. Okay. Then third point is what? Work done in moving a charge over these equipotential surfaces, zero. Okay. Work done in moving the charge on this equipotential surface is zero, because work done is what? Q delta V only, right? So work done by electrostatic force, work done by electrostatic force in moving a charge. In moving a charge on these equipotential surfaces. Equipotential surfaces is 0. Okay, these are some important points as far as equipotential surfaces are concerned. Okay, there are certain more questions that we will be do between electric field and potential difference. Okay, but before that I told you this so that we can use these properties also to solve them. Okay, so let's see. First question I am giving you again. So how to solve this? Let's see. Okay, so suppose that I have a triangle, equilateral triangle. Okay, this is equilateral triangle and each side is L. Okay, and electric field is along x-axis. It's a uniform field, so we can say its magnitude is E. It's like this. It's a uniform field. Okay, so magnitude you can say is E. Alright, this point is let's say A, this point is let's say B, this point is let's say C. What I want VAB. Okay, I want VBC and I want VAC. These three values I want. You have to calculate it. Okay, how to do it? So when you are writing VAB, that means I am looking for VA minus VB, VB minus VC, VA minus VC. If I am looking for this one, okay, then I will be using formula E dot delta R. Here also, E dot delta R. Because I am assuming that at A potential is more than B. Am I correct? Obviously, because B's x coordinate is obviously more than A. X coordinate is least for A, because electric field is along x-axis. Okay, so first which point is coming? A. So because of that reason, A's potential will be more than B and B's potential need to be more than C. Okay, same way here also. Okay, so first of all, if I talk VA minus VB, you can calculate VB minus VA also. There is no problem in it. Okay, so VA minus VB, when we are knowing that, we know that electric field is in this direction, but I am moving along this direction. Okay, so what is the angle between the two? Angle is 60 degrees. Right? So VA minus VB, what we will be writing? VA minus VB will be E. dr value is what actually? L. Dr value is L. So E into L into cos 60. What we are getting? EL by 2. Right? Let's see BC now. In BC means VB minus VC. You are moving in this direction now, like this. What is the angle between E and B then? E and dr. This is dr or delta. This is E. What is the angle? Angle is 60 degrees still. Is it 60 degrees? Or some other angle is there? Tell me. Shall we take this angle? Or shall we take minus 60? Minus 60. Okay. So what will come? Let's see. E is in this direction. Okay. If I am going to take minus 60 over here, then what will come over here? EL cos minus 60. But cos of minus theta is positive value. So what will come again? EL by 2. Is that clear? Why minus I have taken? Because normally the orientation of the angle we take is anti-clockwise. Okay, it is anti-clockwise. But this is clockwise here. You have taken it in this way. Orientation is different. That's why I have taken this minus. Okay. Fine. This was what? VB minus VC. Then what we have? VAC, that is VA minus VC. So in VA minus VC, electric field is also in this direction and you are also moving in this direction. That means angle between dr and E is 0 degrees. So what will come over here? E into L into cos 0. That means 1. So VA minus VC is equal to E into L. Okay? I hope the thing is clear to you. Let's see further what we can do. Okay. Now suppose certain equipotential surfaces I am giving you. Okay, and we have to find electric field from them. So certain equipotential surfaces are given in this way. Okay, so these are equipotential surfaces. It's like this. Okay, let's assume that this is 20 volt. Not 20. Okay, 20 volt, 15 volt, and 10 volt. Okay, and one more I'll make. Here also one more you make. This is 25. Okay, take this as 25. Alright, and we are going to move along x-axis, or the gap between them is given along x-axis and not given perpendicularly. This is x-axis. Okay, so the gap between them, let's say, is given to you as 10 centimeter. This is 10. Obviously this is also 10. And we have to find electric field, its magnitude and direction. Okay, what we have to find? Find electric field, magnitude, and its direction. Okay, what to do? Now we know that these are equipotential surfaces, plane surfaces. Okay, and we know that electric field is always perpendicular to equipotential surfaces, right? And one more thing we know, electric field is always from higher potential to lower potential. This 25 volt is higher than 20. So that means it will be from 25 to 10. But it should be perpendicular to equipotential surfaces. That means electric field will be like this. Okay, and one more information is given in the question. These are 45 degrees. Okay, these are what? 45 degrees. The angle of this equipotential surface with x-axis is also given. Alright, so this is what electric field is like this. Now what I want that, already I know this delta V is 5 volt, but I want that, what is this distance? What is the separation between two equipotential surfaces? Along x-axis I know 10 centimeter, but I want perpendicular, minimum, shortest. So we know that this is 45 degrees. Okay, and this is 10. Right? And this is perpendicular, we already know that. Because electric field has to be perpendicular to equipotential surfaces. So this will be 10 sine 45. But this is in centimeter, remember. Okay, so now I got the value at least for electric field, because I know that electric field magnitude, as I am searching, it is delta V by delta R. Delta V I already know, 25 minus 20, that's 5. Delta R is this 10 sine 45, but centimeter, remember that, okay? So 10 into sine 45, sine 45 means 1 by root 2. So 1 by root 2. Okay, this 10 centimeter, if you want, you can write it as 0.1 meter. So you converted that. So what we are getting here? 5 root 2 by 0.1. That means 50 root 2 volt per meter. That is the electric field value. And what is the direction now? Direction means angle you want. Fine. So if this is 45 degree, this has to be 45 degree also. Correct or not? Perfect. So if this is 45, this is also 45. So what do you say? Electric field is directed at 45 degree from negative x-axis. This is negative x-axis. If suppose we want in vector form, we can write in vector form also. Now E is equal to, value we have already, 50 root 2. Okay. Cos 45 I cap minus cos 45 I cap plus sin 45 j cap. Correct or not? So you get the value. Its magnitude is 50 root 2 and this is only the direction basically. Okay? So you got the answer. So that's all. Okay, that's all for this class. In the next class, okay, we are going to see further, or maybe one more question we can see today. Okay, let's see, one more question we will do. We will find out the locus of equipotential surface. Okay, locus of equipotential surface we will find. Alright, so suppose that we have two charges. One is Q. Okay. One is charge Q. We are going to place it at minus a comma 0, and another one is there. Another charge we are going to keep is minus 2q at a comma 0. Okay, somewhere here is the origin, and we want to find the locus of the surface where the potential will be 0. Locus of the surface where potential is 0. Okay, what are we going to do? I am going to choose one coordinate, any point here. Okay, suppose x comma y, and I am saying potential here will be 0. Okay, so let's find out what is the potential due to q and what is the potential due to minus 2q and add it, right? So potential due to q first of all. So we know that potential due to q